Welcome to the Explainer. Today, we are digging into the physics behind something you do constantly without a second thought, making things turn. Yep, we're talking about the concept of moment, or as you've probably heard it called, torque.
You've been there, right? You're trying to loosen a bolt that just won't budge, so you grab a longer wrench, and suddenly it's easy. Or you push open a heavy door. You instinctively push on the edge furthest from the hinges. Why does that work so much better? It feels like a magic trick, but it's not. It's physics, and we're going to break down exactly how it works.
So, here's our game plan for today. We'll start with the raw idea of turning power. Then we'll jump into the formula to calculate it. After that, we're taking it into 3D, looking at a really special case called a couple. And then, the grand finale, seeing how all this lets engineers simplify unbelievably complex systems.
All right, first up, let's talk about the pure power of turning.
That effect, that push or pull that causes something to spin, has an official name: moment, or torque. Basically, it's just the tendency of a force to make an object rotate around a specific point or axis. It's not just about pushing. It's about pushing in the right way to get that spin.
Okay, so we know what it is, but how do we actually measure that turning power? Well, that brings us right to our second section, the moment formula.
Believe it or not, in its most basic form, it all boils down to this elegantly simple equation. Moment equals force times distance. This little formula right here, it's the secret key to understanding leverage. Now, F is the easy part. That's just how hard you're pushing. But D is where the magic happens. That's the moment arm. And the key word here is perpendicular. It's the straight line distance from the pivot point to where your force is being applied. This is why a longer wrench works. You increase D, the moment arm, and you get way more turning power for the same amount of force. And hey, think about this. If you try to push right on a hinge, your distance D is 0. And what's anything times 0? 0. No rotation.
Now, figuring out that exact perpendicular distance can sometimes be a real geometric puzzle. Thankfully, there's an amazing shortcut called the principle of moments, or Varignon's theorem. All it says is that the total moment is just the sum of the moments from its little component parts. So, what does that actually let us do?
Well, let's compare. Instead of hunting for that one tricky perpendicular D, the principle of moments lets you do something much, much easier. You just break your force down into its simple up, down, and left-right components. Then you calculate the moment for each of those parts, which is super easy, and just add them up. Honestly, for most 2D problems, this is the way to go. It's a total game changer.
But let's be real. The world isn't flat, so it's time to add a new dimension in Section 3. Moments in 3 dimensions. So what happens when a force is coming in at some weird, awkward angle in 3D space? Suddenly, our simple F times D, or even breaking it into X and Y, becomes a huge headache. We need a more powerful tool. So how do we handle that?
The answer is a seriously powerful mathematical tool called the cross product. It's a special way of multiplying two vectors that gives you a brand new vector, one that's perfectly perpendicular to the first two. This is exactly what we need, because a moment is a rotation that's perpendicular to both the force and the lever arm. The cross product was practically made for this job.
And with that, our formula evolves. For 3D moments, our recipe becomes this vector equation, m equals r cross f. It might look simple, but this little thing is packing some serious computational firepower.
Okay, don't let this grid scare you. It's not a test, it's a calculator. It's called a determinant. The top row, I, j, and k, just stands for the 3 directions in space, x, y, and z. The second row is for r, which is just a position vector from our pivot point to anywhere on the line of the force. And the bottom row is, of course, our force vector. You plug in your numbers, run the math, and this thing automatically calculates all the twisting around all 3 axes for you. It handles all the complex 3D geometry, so we don't have to. It's brilliant.
All right, let's move on to a really cool and kind of weird special case that gives us pure, unadulterated rotation. The moment that comes from a couple.
So what in the world is a couple? It's just a pair of forces that are perfectly matched. They have the same strength, they run parallel to each other, but they point in completely opposite directions.
Now here's what's so wild about a couple. Since the forces are equal and opposite, they completely cancel each other out. The net force is 0.
That means the object isn't going to get pushed or pulled anywhere. It's only going to rotate. It's pure turning. And the best part? The moment it creates is what we call a free vector. It means it has the exact same rotational effect no matter where you apply it to the object. The perfect real-world example is turning a steering wheel with two hands. That's a couple.
So why did we go through all of this? What's the point? Well, here it is. This is the big picture, where we see how all this knowledge lets us simplify ridiculously complex systems.
The ultimate goal, the holy grail of this whole topic, is to be able to look at a messy, chaotic system with forces and twists going every which way, and boil it all down to just one single force and one single moment and one single point. This is how engineers can actually analyze real-world structures without losing their minds.
And the process is shockingly simple. It's just 2 steps. First, you add up all the push and pull forces to get one single resultant force. That takes care of all the linear motion. Second, you add up all the turning effects, all the free couple moments, and all the individual force moments to get one single resultant moment. That's it. 2 steps from chaos to clarity.
Let's make this concrete with that traffic light. Before you do the math, you've got multiple weights hanging at different distances, creating a super complicated loading situation on that pole. But after you apply our 2-step process, bam! You can represent that entire mess with just one force and one moment right at the base. The effect on the pole is identical, but the problem is now 1,000 times easier to solve.
And this gets to the very heart of it. We call that simplified system equivalent for a reason. It produces the exact same external effects on the body as the original complicated one. That pole doesn't know the difference. It feels the exact same pull and the exact same twist.
And so we've come full circle. From the simple, everyday act of using a wrench all the way to understanding the complex engineering of a traffic light. It's the concept of moment that's quietly governing how everything rotates in our world.
So I'll leave you with a question. Now that you can see moments and leverage everywhere, what's the most clever or maybe surprising use of it you can spot in your own life? Take a look around. You might just start to see the world in a whole new way.